So today we will keep working on shell balances for heat transport, and lectures, I gotta go through this again. Okay. Okay. So what did we have last time? We actually had a Couette flow. Okay. So this is our Couette type of flow. It's common in viscosimeters. And we actually solved that problem already when we were dealing with momentum transfer. It's just that everything that we dealt with in our chapter 2 and 3 was isothermal. So now we're actually adding something to it, and we're saying, okay, different cylinders. So I'm flowing in between two cylinders. It's an annulus flow. And different cylinders will be at different temperatures. Okay? What happens? What is actually different? So I'm actually wondering what is the temperature profile. I know if I didn't have the flow, essentially I would have a linear temperature profile between the two cylinders. But since I actually have some flow, and with that flow comes some work done on my fluid that is going to add to my energy transport, I'm going to see a slightly different nonlinear profile for my temperature, and I'm wondering how different that is. In certain situations, the more viscous the fluid, like there is actually more friction, and that friction will convert more energy to heat. So in certain situations, that actually might be significant, and I want to quantify that. One of the key things that I just slipped in there, okay, is that I know my velocity distribution. Okay. So I just said, okay, this is the velocity distribution, this is what we derived before, I'm just going to use that. Now, technically, let's go to the extreme situation that I have really large temperature gradient. In that case, and large temperatures themselves, I know that I'm actually going to, at my temperature T0 versus temperature TB, fluid will have different viscosity for different temperatures. We know that we depend on temperature. That's something that we dealt with at the very beginning of the course. We had this dependence. Well, and every morning if you make yourself breakfast that involves heating anything up, if you heat oil in the pan, it's going to start flowing easier, so you change the viscosity. Yeah? So essentially, if my viscosity starts changing based on the temperature, I might actually need to couple the two. In this very particular case, we actually did not have dependence on the viscosity profile on the dependence on the velocity profile on viscosity. There was no viscosity in that formula. That's very specific for this particular example. But in general, I actually might need to, so the only problem I can solve, the only way I can solve the problem in such case is numerical. Okay? At every step on my solution, I basically have to then define my viscosity as a temperature dependent viscosity. So I have to have a lookup table for viscosity based on the temperature and involve that particular viscosity in my numerical solution. So basically, analytically, we have no chance to solve a problem where my viscosity will change based on my temperature in this particular way. Okay? So every time we're solving analytically, we're assuming that we can kind of decouple the two phenomena and solve one first and then use it in the solution for the other. Okay? And that's basically what you do even if you have temperature dependence. It's just that you will do that on every step of your numerical iteration, so you would adapt to the new situation as you go on. So there would be some dynamic change of your viscosity, for instance, if that's something that applies. So that's something that we're going to inherently use in all of these problems, that the two phenomena are kind of decoupled, so I can solve one and then the other, and basically bail myself out this that way. All right, so let's go back. Let me just see my notes. Do I have the particular part where we stopped? No. So I think we were, here there. Here it is. So essentially, just as a recap, so continued Couette flow plus temperature gradient. Okay. So just as a quick, so I had a geometry that is curved. And here I have temperature T0 on the inner cylinder and temperature TB on the outer cylinder. And my outer cylinder is rotating with a constant angular viscosity omega. And one thing that we did, we kind of straightened out this geometry. For large R or small kappa. So now I'm just zooming in and I see just a slit if I have a very large radius. So my curvature to the system is not very large. So I can kind of imagine that it's nearly straight. So then this distance B was kappa R. And I have T0 and TB on different boundaries. And we also linearize the flow in between. So V is equal to 0 on the inner cylinder, and V is equal to omega R on the outer cylinder. I'm not calling this V theta anymore. In my straightened coordinate system, this is X, this is Z, so this is my Vx. So my Vx is essentially omega R X over B. Vz. X is my cross. Now there was a question, how should I know that I should linearize? Technically, we will get to that point where we actually integrate this equation. Technically, you can integrate even with the assumption that you have R, but linearizing, and if you actually plot the difference between the two, it's not large difference. It's 5 to 10% off in one of the points. So it's not a huge difference between this profile. There was like V theta of R is omega R times R over kappa R minus kappa R over R divided by something. Okay, 1 over kappa minus kappa. Somewhere there. But don't quote me on this. Oh, granted, I'm going on YouTube for this, so I hope I did it correct. So in any event, if you actually plot the difference, so for smaller kappa and larger R, it's not going to be a huge difference between the linear profile and this non-linear profile. That's for one. And also, since I kind of straightened out the geometry, conceptually, I'm working in that mode. If I straighten out the geometry, then technically I should linearize the velocity. It's just conceptual. Either way, it's not a huge difference because, again, therefore, up to 10% or so different. And also, it's going to just be easier to integrate the equation. But I think actually, we'll get to that point. It's possible to integrate either way. Okay, so it shouldn't be a huge deal either way. And technically, maybe I did it too early. I just threw it in, right? This is something that you would possibly do near the end when you look at the equation and say, well, okay, maybe I should linearize just to make myself, my life easier. But ultimately, what you should do is whenever you have a question like this in your research, you do a quick sensitivity analysis. and say, okay, well, here are the range of kappas I'm going to use, here are the range of r's I'm going to use. What is the difference between the linear assumption and actual velocity? And if the difference is okay with you and whatever it is that you're measuring, then you go with it. Okay, so that's essentially how you should resolve it in general. So basically, this is a linearized linearized velocity profile. So again, technically not very different from actual solution, but you should verify. So it's really a quick MATLAB plot to verify. And also conceptually, since I straightened out the geometry, I may as well linearize the profile. Fits this straight slit. Because I removed the curvature from the system, so I should kind of remove it from the solution. Okay, so where did we end up last time? When I did the balance for my combined energy flux, that was that vector E. Okay? When I balanced it in this new coordinate system, okay, over a small shell, we got that partial EX partial X plus partial EZ partial Z is equal to 0. So this was last time. So my energy balance gives me this. And it's very similar the way we were doing a Z momentum balance or X momentum balance or whatever balance we were interested in before. And also we analyzed what is actually this EZ, and we also got that this is equal to 0. So this equation essentially comes down to partial EX partial X is equal to 0. Now what is my EX? Okay. It is X component of that energy, combined energy flux vector. So first we have that part, convective part that just moves into my control volume, and it's carrying in kinetic energy plus internal energy, and there was that combination where I split the energy and I'm writing in terms of enthalpy here. So here I also have that pressure contribution times Vx. So that's my X component, otherwise I would have vector V here, plus what's left of the molecular work, and this is X component. So this is basically work of the shear stresses, and plus Qx. So this is just the flux due to the temperature difference itself. So my Vx, I only have Vz, so this part is 0. This here is essentially shear stress as a the stress tensor as a matrix applied to a vector. Right? So when I get the x component of it, it's tau xx Vx plus tau xy Vy plus tau xz Vz. Note that I have a y direction in this problem. So these two are 0, this is a 0, and this is the survivor here, tau xz Vz. Vz is non-zero, tau xz is also non-zero because my velocity Vz depends on x direction, so that partial derivative will not die. Okay. And what is Qx? Formula. Minus k dt dx. So that's essentially what I put in. So I have partial x, okay, of tau xz vz. What is tau xz in this particular case? What is tau xz? dvz dx and multiplied by mu, negative mu. All right. So that's my tau xz times vz, okay, minus k dt dx is equal to 0. This is where I can actually see, so this is basically the differential equation I have to solve. I can see how it's important to know Vz here in terms of x, because then I plug it in, and then I'm solving for temperature distribution, okay? Because if I plug in Vz, which I know, Vz of x, it's my omega r x over b, okay? So if I plug it in here, I will have something in terms of x here. And I'm just going to do this and solve for dt dx. All right, so let's do that. It's relatively straightforward from here. So if I integrate here, I have minus mu. What is dvz dx? I'm going to actually parameterize this, and I'm just going to say, okay, this part is vb, or velocity of the boundary. So this is my vb over bx, okay? So my dvz dx is simply vb over b times vb over bx minus k dt dx. That has to be equal to some constant when I integrate. So my dt dx is, all right, put things on the other side, minus mu divided by k vb over b square x minus c1 over k. And then I integrate. So just a quick comment. So if we had Vz that was a little more complicated function of x, if we had x over b minus b over x divided by a constant, which was that part that we didn't, then this would look more complex, okay? And this itself would look more complex. Overall, we would probably get something that is relatively workable, but it's much less mess this way, okay? And again, the solutions are not all that off from each other. So this would be a more complex function of x, and this would be a more complex function of x, so then integration would be a little hairier, okay? Okay, and then we need to different page. So basically, when I integrate this, I'm going to get that t of x is minus mu over k vb over b squared x squared over 2 minus c1 over kx plus a new constant c2. And I solve this using boundary conditions t0 and tb. So simple enough, this is a parabolic profile. Dot, dot, dot. I'm going to actually just write sort of a normalized solution to this. It's a straightforward thing to apply these boundary conditions and get. Most often, this solution is written as follows. T of x minus t0 divided by tb minus t0. So this is a sort of a normalized temperature. Okay, so normalized temperature goes between 0 and 1. So that way I can compare different cases a little more easily. There's just a way to write the solution. So it's 1/2 mu VB0 VB squared over K TB minus T0. X over B, so X is normalized as well. 1 minus X over B plus X over B. And of course, I do this for TB different from T0. But if they're the same, I'm not going to solve for this temperature distribution, right? Because there is no heat transport. So the number here, there is one number that kind of stands out. It's actually called the Brinkman number. And it actually quantifies the rate of viscous dissipation. How much energy converts to heat, and rate of heat conduction. So this is the number that if it gets too large, this is where you should stop using this equation and actually go solve numerically and look at the effect of temperature on viscosity. Okay? So if there is a significant rise in temperature, one might need to consider temperature dependence of mu. But that's not something we can do analytically. Okay, so this was one of the simpler problems. This was, I believe, 10.4 in your textbook. Just because I'm starting with 10.4, that doesn't mean you should ignore 10.2 and 10.3, which are the solved problems in the textbook. And we will continue with the next example, which is actually in BSL Chapter 10.5. So this is going to be an example where I have heat conduction with a chemical heat source. And it's also going to be a porous medium, so we're actually going to do a little bit of upscaling in the process. Okay? So here is my problem. I have an insulated cylinder, and it's filled with spheres. I have a packed bed. And I'm actually going to look at only part of this geometry, and I'm going to say this is from z is equal to 0 to z is equal to L. And the spheres in this portion of the geometry are catalyst spheres. So there is a reaction occurring at their surface. So those are reactive spheres. and its surface that is reactive. Okay? And they're sometimes called catalysts. So because of this reactive surface, I'm going to have SC, which I think I basically know, in joules per meter cubed second. So this is basically rate of energy produced per unit volume. So this is a standard problem from chemical engineering, but you could also assume in porous media applications that are more close to what we do around here, you could assume that you have a medium that has, for instance, reaction happening on the surface. So this could be during CO2 sequestration. If you inject supercritical CO2 within your brine, it's going to become reactive, for instance, with carbonate. Okay, so that's the reaction that could happen on surface of the grains. Okay, that's not necessarily going to produce energy, but it could actually be in the same context. You could actually have this reaction happening within your porous medium. Okay. All right. So we're going to actually treat this. So this is some cylinder of radius r, and I actually have, so these, the rest of the spheres here are inert spheres. And this is my general z direction. And I'm going to average this because knowing actual velocity distribution through the bed of spheres, I don't know it. Okay, I don't have analytical expression for the velocity though. So I can know it only if I actually go and compute it, which is a 4-scale simulation. It's not an analytical solution. But we will basically average, so we will assume that we actually have sort of like a front moving through, and that front moves at sort of a Darcy velocity. Okay, so that's sort of like a plug velocity. So we will basically treat velocity in an averaged way, since we do not have analytical solution. And quite frankly, even if we have it, it's a lot to deal with if you have a complex geometry. So basically my Vz is going to be my V0 Darcy velocity, or my flux divided by cross-sectional area. So it's Darcy velocity. And it's presumed constant. I'm also the one controlling this in the lab, so I can actually control it so that it's slow enough and that it's constant, and I can compute it based on the way I pack this system. So I have the porosity, I have the sizes of spheres, of course I'm going to make them all equal size and so forth. Okay? So it's something that I think I know. And what I'm actually looking for is I'm wondering what is the temperature as a function of z. I have reaction going on, so there's certain energy that is constantly converted to heat within this volume. Okay? And what I know about this SC, it's something that I measure. What we know about SC is that SC is some coefficient SC1 that I know, and some function of my temperature difference. So one thing that I can control is I can control T0 and T1. So there is a T0 going here and T1. And it's not so far-fetched to imagine that basically depending on the temperature difference and the temperature that develops within this volume, which is T. This is my normalized temperature that develops over here. So T is the temperature along this Z direction, and T0 and T1 are my boundary conditions. So depending on that normalized temperature, I'm going to have the rate of production change. Okay? All right. So this is the stuff that I know. Let's actually now do energy balance. So my energy balance on a segment Z plus AZ, and with some cross-sectional area which is constant AZ. Is what? So I have, this is my volume, okay? Everything is just going in Z direction because I averaged this as such. So I'm just looking at what's coming in and what's coming out, okay, in Z direction. And adding any, so now I actually have that reaction term, so I have to add that into the consideration, okay? So essentially, I have my area, AZ, and EZ evaluated at Z. So that's stuff that is coming into my segment, minus area AZ, EZ evaluated at Z plus delta Z. So this is really 1D, so it's kind of simple. Plus SC, that's my rate of energy production per volume, times the volume. And volume is equal to AZ times delta Z, right? Is equal to 0. Standard procedure divided by this volume. And I'm going to get minus EZ ZZ plus delta Z divided by delta Z plus SC is equal to 0. And when I do the limit, I'm going to get that minus dz dz plus sc is equal to 0. So basically d ez dz is equal to sc. So in the previous case, we had dex dx is equal to 0. Now I don't have a 0. I actually have this reaction term, right? I love this equations that look very simple and then you start solving them. So now is the part that the equation looks super simple except that we didn't write down what EZ is, right? So once I actually write down my combined energy flux and its Z component is 1/2 rho V squared plus rho H, so enthalpy per volume VZ, plus tau ZZ VZ plus QZ So let's now analyze this a little bit. VZ I do have, so that's my Darcy velocity. It's going to be constant here. And then V squared will essentially be VZ squared. Okay. Rho H, so that I will have to actually now write down what enthalpy is. Okay, and I need to have a formula for it. I'm going to give you that formula in a second. And then I have tau ZZ. So I'm going to have tau ZZ is dVZ dZ, right? Since it's a constant, that's the part that is going to disappear. Okay? So tau ZZ has dVZ dZ, and VZ is assumed V0 constant. So this is the part that is going to disappear. I'm kind of trying to look for what's going to disappear first. Okay. And then QZ is going to be my Fourier's law. The only part in QZ, so I'm expecting QZ to be what? Minus K times dt dz. What is K? Which material? We will need the concept of effective K for this packing of spheres. Okay. So basically, what we will need to have here, so it's not the sphere material itself. I have spheres and I have fluid moving through spheres, and I'm averaging things. So the moment I'm averaging, I need the concept of effective thermal conductivity. So this is going to be K effective in Z direction, so ZZ direction, if you will. That's how it's typically denoted. So this is going to be effective thermal conductivity for sphere pack plus fluid. Okay? And in Z direction, that's the only flowing direction. In the other direction, I have insulated system. So the other direction doesn't concern me in this case because I don't have temperature gradient across the sphere pack. And dt dz. All right, we're going to continue with the rest on Monday.
I was late today. I'm late today, and I missed the quiz. Is there any chance I can take
No,
the quiz?
because you knew there was a quiz. I announced it 2 times in a row. Okay. So at this point, because I also went over the quiz, so I basically gave the.
I didn't come.
I went over the quiz, so I can't. It's not fair to everybody else. So I don't know. I wasn't looking. For all I knew, you could have been inside. So I just can't because of the other. Because I went over the solutions. So.
Is there any way I can compensate for this quiz? I'm sorry.
I understand, but like I have no way to. Those are the rules of quizzes, and it was announced. It wasn't an unannounced quiz that you didn't know it was going to happen.
Okay.
So that's it. Quiz is not a huge part by any means.
But there's a 5%.
Yeah, it's 5%, and if you have the other quiz, it's not going to be. It's not going to affect your grade in any major way. Yeah.
How are you?
Great again.
About the project, your function for calculating the perimeter, when I use it for circle, doesn't give the exact perimeter.
How much off is it?
Like 15%.
15%. And if you refine the mesh,
Then the same thing.
still 15%.
Yeah.
Well, no, make note of that. I haven't.
It gives like the perimeter is like 5.6. It's supposed to be too high.
Well, you can correct it manually. Certainly.
Yeah,
Then you do still need the straight line, right? No, straight line is open boundary, so that's not the.
Yeah, it doesn't matter.
Oh, the image just.
But that's something wrong. That's not normal.
I don't know.
So did you
I don't
report
know.
to? Let me see.
Yeah, I asked for him about that.
Okay.
And
Because that's not. It's not. It's something's going on. It's not something that is
I
supposed to.
checked online the core, the CPU. It is 10 years old. The CPU.
10 years?
Yeah. I checked on the computer. It is Core 2.
Wait a second.
Okay.
You have computer that Sohail used to have.
No.
No? Whose computer?
Javier used the computer that.
Sohail.
Yeah.
And you have whose then? Whose was it before that?
I
Who's
don't
the
know.
second? That will be because Sohail's is definitely
Yeah.
younger.
Javier's computer is much better than mine.
Okay, yeah, so
Yeah.
I don't know whose you got. Because that might be the next one to change. So that was, we dealt with that somewhere early. Had a list of computers. No. No, let's see that.
Yeah, actually,
Because if it's so old,
yeah. Javier told me that it is the same one when that he used when in high school. Yeah.
oh boy. Wait a second.
Yeah, it's.
I
it's
didn't know that
really
I had
terrible.
so old. Okay. Trying to figure out whose was it. Ningyu has Frattura. And how are you calling that computer now?
The computer name.
Yeah. So this one is the. Oh wow, yeah. This is Fernando's old computer. SB means so MP is me. This is inherited from Stephen Bryant. So that must be Fernando's computer. Mm-hmm. Either Fernando's or Rodolfo's. Because this one is newer one. This is so these are the next. So this is one of the oldest ones. Okay. Yeah. Okay. So this is the next one up for changing.
Oh.
So it's yeah. For now we'll use it, but again, it shouldn't still do what. I mean, unless it's about to die.
Right now, it should be. Sometimes it will be black screen and red screen or colorful screen. At least
Okay.
once every day, actually.
Okay. Oh, that's the new gotcha. Okay.
Yeah, the computers are the properties of our university or our research group.
A research group.
Oh.
So university does not provide for computers.
Oh.
The only computers university provide is TAC
Oh. Yeah.
or the computers that are in the student lounge.
Oh.
Okay. All of the other computers that you see, they're essentially purchased by funds for research grants.
Okay.
So when you apply for a research grant, you typically put an expense on there called a computer.
Yeah.
And if you don't have a research grant that allows for that, you can't buy one. I mean, that's how it works. So even like computers like Leilani's, like I purchased Leilani's computer.
Oh. Okay.
Which is technically not research, it's something that technically should be provided by the department, but the question is how much money does the department have? So the way it's actually we are at the state university, but finances for common stuff at the university is not all that high. So it all has to be supplemented by research. So in terms of the overall UT budget, only 10 to 15% comes from state.
Oh.
And that's why this is a state university. But like, I don't know, if you go to Croatia, it's not 100%. Okay. Or maybe like something like 90%.
Oh.
So on all of the research grants too, so we are all supplementing the university budget because otherwise university won't be able to function. Because by the time university pays salaries of people working here, there's not much left to run the electricity bill. So essentially, the way it works is that every grant, so when I apply to Department of Energy for a grant, it has an overhead. So I'm asking, so in grant, you create a budget. I'm asking certain amount for students, for student tuition, for part of my summer salary, because I don't get salary in summer. I get only for 9 months. Then for some, any kind of experimental equipment, computers, like anything that is needed for the execution of the research project. And then that's a sum. Okay. Then there's first overhead is called Fringe, which is 27% on top of your salary, is for or any salary. 27% on top of it is for health insurance and things like those. And then there's a number, and then 56% on top of that number is charged as overhead. And that overhead goes to university.
Oh.
So that's literally for keeping this office running, cooled, heated. That's university expenses. So that's the second portion of the university budget.
Oh.
That comes from the overhead of all of the research grants. So the university of this size, that's how you finance things. And then, of course, tuition. So in the budget of the university, there is some that comes from state, which is not much. Then tuition. Tuition essentially goes to professor salaries.
Oh.
And any kind of investment into classrooms. And then there's this like regular stuff that is essentially covered by the overhead on grants.
Oh. Okay.
So essentially, for any kind of computers in the group, you have to plan it in the budget.
Yeah.
So if you ever get to the university type of position, you actually have to. That's one thing you have to learn, and nobody really teaches you how. Like you show up as faculty, it's like, oh, I gotta provide for computers. Oh, okay, because they kind of think that should be provided, but it's not.
Oh.
So yes, computers like TAC, yes. I mean, there's a lot of money in there in terms of providing for all of the services that they do. But they also have to finance themselves from all kinds of research grants and whatnot. But I mean, it's a whole lot of money to replace, for instance, all of the nodes. And still, actually, if you think about speed, all of their computers are consistently better than anything else we actually have in the group.
Yeah.
And the reason is they replace supercomputer nodes are replaced every 3 to 4 years.
Oh.
So when they replace the entire thing because speed is a deal there.
Yeah.
So anyway, I'm gonna ask Tim. So I essentially need to ask Tim if that computer is about to be dead. If it is, and if it is, so he needs to run diagnostics.
Yeah, actually, I will buy a laptop. But
that's your personal.
Yeah.
Sure.
But
So
if the office computer doesn't work well, it is a little inconvenient.
right.
Yeah.
Right. So and that one still, and often like with the laptop is like you got a computer that you don't do that to, right? So in that sense, laptop. I mean, point of the laptop is to move it.
Yeah.
I purchased this laptop as pretty good, like it's a MacBook. So those are actually computational laptops. So it's not the thin one, but it's still relatively portable. I don't find it a problem.
And the Mac system is very similar with the Linux system.
Yeah. So basically, you have something called terminal.
Can you connect to?
Yeah.
Yeah.
You have something terminal. So you use all of the commands that you would normally would.
Yeah. Oh.
Okay. So this is just like a terminal. This is a Unix terminal. Just like your Linux. Unix is the original name of the system. The operating system is Unix. UNIX.
Yeah.
Linux is one flavor of it.
Yes.
So the type of Unix that is here is slightly different than Linux, but there is similarities.
Yeah.
Right? So most of and there's a couple of things that are different, but it's not like overall it functions just like a Unix or Linux system would.
And I know that the OpenFOAM, Light and CFDM both have the Mac versions.
Yeah.
But Nianyu told me that actually I can run it on Mac, but I cannot modify the codes of OpenFOAM.
Well, okay, so in order to modify, so when it has a version for Windows or for Mac or whatever, there's this in these guys it's called DMG. It's like the image from which you install. Okay, so in that sense, when you have something that you just like install by clicking on it, okay, that means that it's already pre-compiled.
Yeah.
Right?
Yes.
So then its installation is much quicker, right? Because all it does, it moves executables to a specified location, and that's it, right? Yeah. And then you can find and run. So every time you install software like that, just by executables, you won't be able to modify.
Oh, yes.
Right?
Yeah.
So if you want to be able to modify, you actually have to get the source and compile it yourself. Okay?
Yeah.
But for that, on a Mac, you will have to have something like there's like a compiler suite called Xcode. Okay, so you'll use that Xcode and install, and then you will have all of the compilers and everything that typically developers use. And that compilation might take 2 hours.
Oh.
Right, just like you compiled now everything. Okay? So it's the same process then. Right?
Okay.
So yes, you might actually have. The benefit of these things is if you just intend to run software, then it's fine. Then you don't need anything else. If you intend to actually modify something, then you have to behave like a developer and install from source. So I'd say for now, right? For now, just use it as an executable. But if you expect immediately that you'll have to go and look at the code and how it's doing what it's doing, you can do that for now in TAC.
Yeah.
Right? if you want to understand like how the code looks like and all that stuff. And then if you realize, okay, it seems that I'll have to change this on a regular basis, then install it, then go through 3 hours of compilation. Or if it's when it's 3 hours, that's good. But often there's little something. The problem with most compilations nowadays, they're getting better, but also the software is getting bigger. I mean, that's something just like you did, like install something for half a semester. I mean, we all went through that. So you have to just, that's how it goes. And most of the time, basically all of the software has certain dependencies. So the problem is not just the software that you're installing. The problem is that it depends on 5 others. And of course, you learn as you go. Like you start compiling and then it complains about one. Then you go and find it and you install that one. And then by the time you figure out, it's not just installing it, you also have to install it in a location that it's going to be able to find. And then there's like all these, then you figure out that one, then you keep going, and then it fails on another one. Then you go and install that one. So that can take for like 2 days going and installing one by one. And if you're in a situation where, like we are here, that for Office Computer, you're not the one in charge of the computer, so you're not the admin, then you have to, every time you install something, you have to actually ask Tim to install, right? Suddenly, like there's this. But UT is very strict about that. Even I cannot get the administrative password. So that's the security.
Yes.
And I see where it's coming from. I agree with it. At this point, I used to be actually an admin when I was a student for my group. Even though I didn't know much, my advisor allowed me to meddle with the computers, to install things. Essentially because we had a problem. We had like a department with like 140 people. Even more, and only one person doing the administration. So that admin was just way too busy. So then they allowed it. But like here, no. And even though I'm faculty, I cannot get the admin. And that's for the security of entire university. Because if you have one vulnerable computer, entire university is vulnerable. And these things are way different than 15 years ago. So, here we go. Oh, no. So it's a video driver. So he says that that's
Video driver.
So there is one problem with hardware, and this is something that we've had issues for a long time. Vendors, they, like Dell, they make computers, and they don't necessarily disclose drivers other than to Windows. So they come with pre-installed Windows systems, and Linux community is the free community. Everybody else is like commercial. And they often, then Linux developers don't necessarily know the details, like all of the details of how to run a screen. Those are video drivers. So video drivers don't exist for Linux. So the Linux guys have to go and guess them. So they make their best guess, and it's actually not far off, but it's a little off. And there's always a lag. So that's the incompatibility between Linux and the hardware. It's essentially because of the trade deals of some sort. Dell says, I'm gonna release the driver only for Windows,
Oh.
but not for Linux because Linux is not going to pay me anything.
Yeah.
Linux is free. And because of that, Linux has to guess what the drivers are.
Oh.
And sometimes those drivers are never really, really good. So that's apparently what's causing the lag.
And how to
Welcome to Linux. So,
how to deal with this problem?
the best we've been able to is when you're buying a computer.
Yeah.
I asked him, can you go do a little bit of research that whatever we are buying is compatible with Linux?
Yeah. Actually, if
this computer is an old Windows computer, so that was never done. Right?
Yeah.
Because if it's 10 years old or however many years old, it's not a computer where there was intention to convert it to Linux. Though if it's this old by now, Linux should have drivers for it, but you never know. And part of it is that hardware changes so often that that's a problem, to keep up with all of the hardware that is out there. Right? Having drivers for everything. Not sure why we need that much variety, but but we have it.
Yeah.
Okay. So he's working on it. He's like, I'm thinking it's video driver. So maybe it's not about being old. It's about the video.
Okay.
And he says he asked you to log out of everything.
Oh.
Yeah. So.
Yeah, now I'm thinking about buy what kind of laptop actually. Actually I want to buy the ThinkPad P50. It is a mobile workstation.
Mm-hmm.
Yeah, it means that the computation performance is very good, but its disadvantage is very heavy, a little heavy actually.
Mm-hmm.
And if I buy a Windows computer, I would install the both the Linux system and Windows system.
Mm-hmm.
And but if you convert between these two systems, you should turn off the computer.
Yeah.
Yeah.
Yeah. That's a
And
little messy.
yeah.
I mean, again, you could have a virtual machine, but virtual machine is, I don't know that there are integrated ones that do both at the same time, but the problem with the virtual machine is that it's on top of this operating system. So
Yeah. Actually,
there's a slowdown for the
Yeah.
virtual machine.
My laptop, I have installed the virtual Linux system,
Mm-hmm.
but my laptop is not very good, so it is very slow to run the Linux system.
But
The
you
virtual
could
Linux
use,
system.
but MATLAB is something that you could have on either.
Yeah.
So MATLAB shouldn't be a problem because you can have it
Yeah.
on your Windows side.
Yeah. Yes.
It doesn't have to be in virtual.
Yeah.
So depends, I don't know, write down what are you going to use. So what I like about Mac is that the two sides are together, integrated. Like I
How
don't have
about
to switch anything off.
The computational performance.
Computational performance is pretty good. It's just that the moment you're buying a Mac, it is more expensive than equivalent Windows machine. It is a little more stable, so Max charges. And when you need something like, there's no way out, but $80 for the charger,
Oh.
right? So these pieces, small pieces, why is this piece $30? I don't know.
Oh.
Right? So there's like all the little accessories for Mac are also a little more expensive.
Yeah.
And I don't think that they're all that high quality. Actually, one of them, the reason why I'm buying this one is this one went bust. So anyway,
Yeah.
that's the reality with Mac. So there's it's a little pricey because it's a little more slick and well designed. Again, I decided to go with it, but it's not without its problems, because even though I have Microsoft products, like I have Microsoft Suite for Mac, okay, it's never perfectly compatible with Microsoft from Windows.
Oh.
It's annoying as hell, but like I get, for instance, so then people send me PowerPoints with formulas specifically.
Yeah.
So I'm not even using Mac software. I'm not talking about using Keynote. Keynote is the PowerPoint for Mac. Okay? I'm not using it all together. I'm using Microsoft because people send me Microsoft stuff and I want to collaborate, right?
Yeah.
And then students send me slides and I go to show them and the formulas don't show, or they show like scrambled. So there's always a little bit of that. There's no free lunch. It's like, kind of like, so you just have to decide what do you want to deal with. I personally, this turn off to get to the other system, that really, really annoys me, right? But then Rodolfo, I don't know if you ever met Rodolfo, the student that was here before. So he's now in Brazil, though he's about to graduate, so he's going to show up next semester. He happily goes back and forth. Like, he's okay with that. He doesn't matter. And he didn't want a Mac or anything like that. No. Lenox and Windows. So different. So you have to decide that for yourself. I can't decide it for you.
Yeah.
Right? Again, you will be dealing with Linux systems. Mac is a Linux system, but that doesn't mean that, like, if you want to install something on a Linux and install something on a Mac, there will be slightly different issues between the two in terms of what software is already there, how things, like, there's always small differences, right? It's never whereas if you have a Linux, well, your Linux is probably going to be the same, especially if you install Ubuntu, which is what we have here. Yeah. It's going to be very similar to what you have in the office.
Yeah.
So I don't think that there is an easy answer.
Yeah.
You have to kind of like read about it and then at some point just decide. Yeah. Because there's always something that you'll have to deal with. There's always that, right? Yeah. So it's not, sorry, but
it's okay.
So for instance, I have found that, like, I bought this to be a computational machine. I'm using it for teaching. It's my same computer. I don't have a computer at home other than this.
Oh.
So I don't have a workstation so I kind of I like using the same computer for everything. Yeah. But that means that I end up not doing any major computation on this. Because if I start doing computation, I have to leave it open without So in essence, me purchasing this MacBook for the relatively essential tasks I'm doing is not necessary. Right. I do like bigger screen, so there's that.
Yeah.
But yeah. So I don't know if that helps.
Yeah.
So my point is that if you're gonna end up using your laptop, for the most part, if you end up using your laptop just to work on homework and connect to a computer that is doing simulation.
No, I want to do some simulation on my laptop.
Okay, so then you have to kind of evaluate. So then go also ask. I mean, this is pretty good computational machine. It's by now 4 years old, so it's not the newest one.
4 years old.
Yeah, so it's not the newest one. About this Mac. But there is, for instance, it has, I don't know that the processor is much faster, but it has 16 gigabyte memory, right?
It's still much faster, actually.
Right, so it's still pretty fast. This is still a pretty, and these days, like, processors don't, they kind of reach the cap, so they don't get much faster. There are 3.5s out there, but
Yeah.
in terms of, and then there is a video card that is pretty good, which is something I care about because I do visualization. So this video card has 2 gigabytes of memory.
Yeah.
Yeah, and for visualizing stuff, and you will do visualization as
Yeah.
well. That's kind of important. So I would say having good video card, no matter what computer, is pretty important. If you install Linux on it, there might be some issues with the video card versus that video driver. Okay, so if you are buying computers with better video cards,
Yeah.
are gamers' computers.
Yes.
So actually, Windows does make sense in that sense because XPS, I believe, Dell's XPS is a little gamer's laptop.
Yeah.
That is likely going to have a pretty good graphics, right?
Yeah.
So that's something. But then before buying one, just make sure, like, what do people say about the Linux installation on it? Or when you look at Dell websites, sometimes there are computers that come with Linux.
Oh.
So that computer is guaranteed to be compatible. Okay. So those are little details. So I would go for, regardless of what you end up, I would go for a pretty good graphics card. So you can do some visualization on your computer.
Yeah.
And then memory, I would do minimum 16 gigabyte if you really want to have a little workhorse.
Actually, the latest version of MacBook is 16.
Yeah, it's still
The
16.
memory,
It didn't
yeah.
increase much. And the only other thing that I've seen, what was the computer store? UT. I've seen just now when I was picking this up, they will have 1-day sale.
Oh.
So check what the price will be when you do 1-day sale UT. So you can pre-order, and if you buy it on November 17th, it's going to have some, I don't know how much off. I didn't try.
Okay.
So that might make a difference in the budget. So check the Mac website versus computer store here on campus.
Oh.
So there's Mac website, right?
Yeah.
And then there is this, I don't know if it's...
This is the campus computer.
Yeah, this is campus. This is University of Texas campus computer store.
Oh, okay.
So they seem to have some sort of deal.
Okay.
Again, I don't know. I haven't tried it. Though I've been actually thinking, these days, like, if you have a computer that is 4 years old, you can start thinking about replacing. But they don't build computers to last more than 5 years. It's like, but then my last one though. So the computer before this, I had like a 13-inch MacBook, and that one is still alive. So now it's like 8 years old. My husband uses it at home, but God, it's slow. So when you get on it, like, it's still working, because at that time, I was like, it started kind of like being a little slowish. And I'm like, again, computers max 5 years, and you gotta change them. Let me go buy another one. Because I thought that one would just like die. Still didn't die. That one's well made. It still didn't die, but it's slow. Like the other day I got on it and I'm like, wow. I don't know how this thing... Anyway, here comes my phone. Yeah. Okay. That's okay. All right.
Yeah.
Okay.
Thank you so much.
No.
Stupid question. So I was doing this one, and I noticed that this vector E starts at E2. Should it be E1?
No, well, it starts as E2. Whatever it starts as doesn't matter.
I mean, if it was on the test, could I make that E1? Because I figured that like
It really bothers you? Sure. I mean, otherwise it's just numbering, right?
well, it's harder. It seems like to me. But I just wanted to make sure like I did this where I was like ON and not like ON squared. So this right here, I just have it percent.
That's
I wanted to see how it worked.
that's fine. Why is it O of n? So here within the loop, right?
Yeah.
We have 1, 2, 3, 4, 5.
So what does that make it?
5n. That's O of n.
Okay, so that's
Right.
OD. And then this one down here should be. It's actually just.
It's also
It's
like
also
you have 1, 2, 3 times, right? And 1 division, so 3.
Okay. But it looks good, right?
Yeah.
Okay, awesome.